Good morning, ladies and gentlemen. Section 2.3, continuous functions. What is a continuous function? That's what we're looking at today. Continuous function is basically, if you can go from negative infinity to infinity, plot a whole bunch of points for a particular set of ordered pairs or a whole relation of ordered pairs, and you can connect them from negative infinity to infinity. With your pencil, you're drawing, you're connecting the dots, and you never one time have to pick up your pencil to move across some type of break at any point in time in the graph, okay? Now, it's really important to know if a function is continuous in calculus, because if the function's not continuous at a particular spot or something, there's operations we cannot conduct in calculus on that. So it's really important, and we had to know stuff about limits before we talked about continuity or how a function is continuous. Okay? What I'm going to do is I'm going to reveal 6 graphs here. I already pre-did them to try to shorten up my video for you. I pre-drew them, hit pause, and I want you to sketch these in your notes. Okay, so now hopefully you have all these sketched in your notes right there after you pause. And number 1, okay, basically it's got this little hole in the graph, and it looks kind of like a wiggly and squiggly one. And technically the name for this first one, this is called a removable discontinuity. And I'm going to call it a removable disco, okay? Number two, we have a vertical asymptote at x equals c. I wrote my equation of my asymptote. That's at some number c, just like I have a hole here somewhere at c in number 1. And when I'm looking at this, these are known as an infinite discontinuity. Okay, it's an infinite discontinuity. Number 3, there might not be one asymptote in there. What I did was I'm just trying to get you to picture maybe the tangent graph, maybe the cotangent graph, maybe the secant or the cosecant also have these types of issues where there's a whole bunch of vertical asymptotes again. Okay, again, it's an infinite discontinuity. However, you got to understand if I'm within a particular range between here, okay, my tangent would be continuous as long as I was within a particular interval. Just a little keynote. Number 4 here. Number 4 looks a little bit different here. Number 4 is really a piecewise function type of function, and what you're looking at right here is kind of known as a jump. It's a jump discontinuity. Or some people call it a step discontinuity. Just like that greatest integer function that we did in the first unit. Okay, number 5 looks a lot like number 1 because it has that hole in there. But number 5 is not continuous for a different reason than number 1 is, okay? And number 6 down here, it's just kind of like a square root function. And although the square root function is continuous across its domain, I also need to understand when I'm looking at something from negative infinity to infinity, c in this case is not in the domain of that function because it's way over there. My function doesn't even get graphed there, okay? So we're going to take a peek. We're going to take a little peek at these and say, how or why are these discontinuous at x equals c? Okay. Again, when I'm looking at numbers 1, 2, and 3, numbers 1, 2, and 3 are, I guess I could throw 6 into this mix too, but they are not continuous for a particular reason. They are not continuous because f of c does not exist. Okay, C is not in the domain of the function. Notice C, I have vertical asymptotes in 3, I have vertical asymptote in 2, and I have a hole in 1. Okay, a removable, excuse me, a removable discontinuity. We're going to learn probably tomorrow that we're going to be able to fill that hole and make it potentially continuous. And actually, you've done that in Algebra 2 and Pre-Calc already. Now, when I'm looking at number 4 is not continuous for a different reason, because I can see, because this dot right there, that's a solid dot we have there. F of C does exist, okay? However, you can see there's this big break in the graph right here, okay? And that's really what we're looking for. No breaks, no hops, no jumps in the graph for any reason. And number 4 is not discontinuous because C is in the domain. Okay, number 4, f of C does exist. However, the limit as x approaches C does not exist. So I should throw that in here. The limit as x approaches C of my f of x function does not exist. Okay, and we can see that because if we're tracking it in from the left and we're tracking it in from the right, we are approaching 2 different values, so that limit does not exist. Number 5 is a little different than numbers 1 through 4. Number 5 is discontinuous. Well, look at it. This is kind of weird. F of C does exist. There it is. That's my f of C up there. The limit as I approach C exists because as I come in from the left, I'm approaching here. As I come in from the right, I'm approaching here. So f of C exists. The limit exists, but this one's not continuous because, let me get that off and try to extend my page. That one doesn't exist because f of C is unequal to the limit as x approaches C, meaning the functional value of C up here is unequal to the limit value of C. Because they're different, it's a discontinuity in there, okay? So if it's a discontinuity, the function is not continuous at C. So, whoa, I extended the page. I didn't want to extend the page. So I'm going to go to the next page. We're going to be talking about what's called the continuity test. The function f of x is continuous at x equals C if and only if the following 3 statements are true. Okay? So what has to happen? 3 things have to happen. These are rules we kind of need to go through to prove something is continuous. Okay? Number 1, f of C has to exist, which means C has to be in the domain of f of x. When I plug that value into the function, it must output a y value for me. Number 2, the limit as x approaches C of the function has to exist. So not only does the functional value have to exist, the limit has to exist. And number 3, the limit value has to equal the function value. Okay? So all 3 of these things kind of piggyback each other along. And I wrote a little note here. Note, to be continuous, all 3, and I did all 3 in capital letters because it's important. If one of these 3 things are not true, the function is not continuous. All 3 must be true for the function to be continuous, okay? Well, what is the definition of continuity, okay? Now, continuity at a point, that's what we're talking about. We're talking about that point C. Well, sometimes we'll have a specific interval, okay? Sometimes we'll be talking about negative infinity to infinity. Sometimes we might be talking between 0 and 4. And when I'm talking about a particular interval, we have interior points and we have end points, okay? And a function, y equals f of x, or a function f of x is continuous at an interior point of C. At an interior point, we're going to call it x equals C. of its domain if the limit as x approaches c equals f of c. So basically, this is restating number 3 from the slide before, okay? So if number 3 is true, that means the functional value exists, it means the limit exists, and because they're equal, I am continuous at that point. A little bit different when I talk, well, not a little bit different, but when I'm talking about an endpoint, a function is continuous at a left endpoint A. Okay, so we're saying a left endpoint A because this is my A value here. This one right here, this is my left endpoint. Okay, and it's also, this will make sense when I draw you a little picture here. In order to check if the limit exists at the left endpoint, I need to approach it from the right side, or if it's continuous at the right endpoint, and we're going to call that endpoint B. So this one right here, in this case, is my right endpoint. But to make sure the limit exists on the right, I have to approach from the left. Okay, just like I have to approach A from the right to see if the left endpoint exists. Okay, so it's continuous at a left endpoint, or it's continuous at a right endpoint of its domain if the limit as you approach from the right equals the functional value, or the limit as you approach it from the left equals the functional value, respectively. Okay, what am I talking about? In general terms, okay, talk to a bunch of people. They're like, I don't like all this math symbols and all this gobbledygook we got going on. But in general terms, what this basically means up here for the endpoint is if f of x has a hole at an endpoint, then f of x is not continuous at that point, okay? What? I don't get it. Well, let's draw a quick little example here. So if I drew a cute little example, let's say I'm at 1, let's say 2, 3, extend that over and say 4. Let's say I'm right here, and I came down, and I'm right here. Okay, notice the right endpoint is an open circle, therefore this is not continuous at x equals 4 in this case. Okay, it's not continuous at x equals 4. So, next slide. Do not worry about this if you want a little bit challenge later, where I'm not going to go through graphing all this because it's a waste of our time on the video. I have the graph for you right over here. What I'd like you to do is I would like you to pause the video quick, and copy that graph into your notes, and then we are going to ask some questions or answer some questions about that graph. It's a typical AP type question right here, okay? So as we're going through, bottom line, what we're going to do is we are going to be looking here. The first one I'm going to be looking at here is, does f of 0 exist? Does f of 0 exist? Well, here's 0. F of 0 equals 1. So I can see f of 0 equals 1. So yes, f of 0 does exist. That's rule number 1. We're checking for continuity. We're checking for continuity at the point 0 right now. So does the limit as f of x, does the limit of f of x as x approaches 0 from the right, so as I'm approaching that value from the right, does the limit exist? And the answer to that is yes, the limit does exist. What is the limit? Okay, the limit is 1. Okay? And does f of 0, does the functional value here, does that equal the limit as I approach from the right? Yes, it does. Okay? So what does that mean? That means f of x is continuous at 0. Okay? Is f of x continuous at 0? Yes. Now, I could have popped this graph off. I could have jumped straight down to number 4, and I could have had you look at this via what we just said. Is it continuous at x equals 0? And people would have said, yeah, it's a closed dot. It's an endpoint. Therefore, yes, it's continuous. However, in this class on the AP test, lots of different things, okay? Typically, it would say, is f of x continuous at x equals 0? That is a yes or no question. After that, it says justify your answer, state your reasoning. That means give me proof. Prove to me that it is continuous. The only way you can prove to me it's continuous are via these 3 steps, okay? A lot of people are going to say, well, can't I just jump down to number 3 and state it? Well, technically we will, but you're wasting your time, okay? And I'll have an example of that. So is it continuous? Yes. What I need to write is f of 0 equals the limit as x approaches 0 from, in this case, because it's an endpoint limit, from the right of f of x. So because the functional value equals the limit, it is continuous, okay? Now let me squirrel down here to say number 5. Is f of x continuous at x equals 4? Is it continuous at x equals 4? I'm hoping you're going to tell me no. I'm hoping you're going to say, no, it's not continuous. Justify your reasoning. Tell me why it is not continuous there. It's pretty easy, okay? Why is it not continuous right here? What's going wrong? Rule number 1 is going wrong. It is not continuous because f of 4 is undefined. Because it's undefined. Another way to say that is x equals 4 is not in domain. Okay? That is a justifying your reasoning. This would be a 2-point problem, a 2-point question on a test. 1 point, 1 point. Okay? Without the reasoning, it's called a bald answer, and you do not get full credit for it. So what I'm going to do is I'm going to pop over here to the next slide, and I'm going to just give you a second. Okay, hit pause, ask or answer 6, 7, and 8, and I will be back, and we'll go through that. Okay, I'm back. F of 2. What is f of 2? Well, I can come right over here, and I can say f of 2. Oh, f of 2 equals 3. What is the limit as I approach 2? Notice this is a 2-sided limit because I'm in the interior of this function. What is the limit of f of x as x approaches 2? Well, if I'm coming in from the left, what's my limit? 2. As I come into the right, what's my limit? 2. The left hand and the right hand limit exist. I don't need to write that out on paper. I can look at this graph and say, why, yes, the limit does exist. The limit is 2. Is f of x continuous at x equals 2? Is it continuous? Would you be able to connect all these lines in here and make all these dots without ever picking your paper up in this middle section? And the answer is no, it is not. It is not continuous. Justify your reasoning. It's pretty easy. F of 2 is unequal to the limit as x approaches 2 of f of x. Okay? The limit is unequal to the functional value, therefore it is not continuous. Okay? So, let me get rid of this little bit. Well, what value should be assigned to f of 2 to make it continuous at x equals 2? Well, that would be pretty easy. What would it have to be? F of 2 would have to equal 2. Because if f of 2 equal 2, well, functional value would equal the limit. Bada bing, bada boom, it's there. Is f of x continuous at x equals 1? Why or why not? See, justify your reasoning. No, it's not. Why not? Because I said so. No, grabbed the wrong thing. Why is it not? Because the limit as x approaches 1 of f of x does not exist. Justification, that's my proof for my answer. Okay, why not? Well, the limit as I approach to the left is 0. As I approach to the right, it's 1. Left hand doesn't equal the right hand. Therefore, the limit does not exist. We can see that right in the graph. At what values of x, 1 or 2, perfect AP question, is f of x not continuous? So let's take a little gander. Take a little gander at that. Where is it not continuous? Why don't you answer the question for me? Right? If you guys were here, we could do that. It is not continuous at x equals, it's not continuous at 1, it's not continuous at 2, and it is also not continuous at 4. It is not continuous at x equals 1, 2, or 4, okay? So we're getting pretty close to being done here. I got one more slide, and then I'm going to break this into a 2-day, okay? Here we go. We are going to find the points of discontinuity. And then after we find those points, we are going to identify the type of discontinuity, whether it's, is it an infinite discontinuity? Is it a domain discontinuity? Is it a removable or a whole? Is it a removable discontinuity? Now, think about this, the domains. Okay, I want to come back here. I'm going to shoot back to my first graph. Okay, and I'm going to look at this. My domain, number 1, is a domain discontinuity. Okay, number 6 is really a domain discontinuity because they're not in there. Okay, 2 and 3, those would be infinite discontinuities. Okay, they are domain issues. 1 could also be a removable discontinuity. Okay, so I guess I should say number 1 wouldn't be a domain. Number 1 is a removable discontinuity. 2 is an infinite discontinuity because if a hole, I can always typically go back and fill a hole. Okay, so let's get me back to about where I was. I think I was here. And we're going to look at this little bad boy. Well, a rational function. Let's look at this little pot licker once. And that's actually x plus 1 over, because I don't know, I ain't going to guess and check. I'm going to look at this bottom and I'm going to factor that rat. And I'm going to look at that like, oh crap, I'm really bad at factoring. You'll get good at it. You have to. Oh, last term's positive. That means my signs in here are both positive or negative. Middle one tells me what they are. Minus, minus. If I put a 3 and I put a 1 there, I get a -4 in the middle. Okay. So, where are my points of discontinuity? I am discontinuous at x equals 3 and x equals 1. Well, what type of discontinuities are those? Those are infinite discontinuities. Why are they infinite discontinuities? Because they are vertical asymptotes. How do I know they're vertical asymptotes? Because none of the factors reduce. Remember, if a factor from the numerator and denominator reduce, it's a whole. It gets these 0 over 0 because it has a common factor top and bottom. We're going to look at number 2. Okay? Is this, oh crap, I forget. Oh yeah. Absolute values look like V's. So what could I do here? Well, I could make myself a sketch. And I could remember my translation rules at -1. That shifts my vertex over here at 1. And I got a V, and I got a V. I need arrows. There's my graph. Well, is it continuous? Or are there points of discontinuity on number 2? Nope. This little pot licker, it's continuous. It is continuous. Woo, yay, I'm continuous. Ooh, but there's a trouble spot on there with a calculus operation. Well, we'll run into that later on. We're not to that point. I'm going to look at number 3. Actually, let me get rid of that. I'm going to extend the page up because I want to look at number 3. Well, how can I see this? Well, again, oh crap, that's why those parent functions are so stinking rotten important. Well, what does this little guy look like? Well, if I had one of these, oh, if I had, and I got a 1, well, I know where my vertex is because if I put, when x equals 1/3, if I put a third in there, I get 0. So about right there is my beginning point, right? If I put points less than a third in there, like 0, oh, I get negative, and then it's a hook. So what are all the points of discontinuity in here, or are there points of discontinuity in here? Okay, are there? Are they? And if they are, what kind are they? Infinite domain or removables? Well, let's check it out. Well. Oh, yes, there's lots of discontinuities. Well, how about the discontinuities for all real numbers x that are less than 1/3? If they're less than 1/3, okay, they are not in the domain of the function, which means these are domain discontinuities because anything smaller than a third is not in the domain of that function. 1/3 will go in, put a third in, I get 0, I get an ordered pair out, but any number smaller than a third, okay, this little point is 1/3 on my half, 1/3 on my x-axis. Anything smaller than that is an issue, okay? And the very last one, tangent x. Well, this has all kinds of infinite discontinuities. How do you know that, Mr. Kruger? Mr. Kruger knows that because he knows his parent graphs. And what I can say is, I remember when I went forward with a tangent, or if I went back with a tangent, and I know this point right here is pi over 2 and pi over 2. See, I just know what my parent graphs look like. In every multiple of pi over 2, meaning next one, 3 pi over 2, next one, 5 pi over 2, next one, 7 pi over 2. What happens at every one of those little rascals? Right here, one of these guys happens every time. And in the middle of that little bugger, we get a whoop-de-woo, a whoop-de-woo, woo, 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 woo. See how this is not on a particular interval? So they want to know where are the discontinuities for all x values. This is discontinuous at all values. They are discontinuous at x equals multiples of pi over 2 plus pi n. Notice these are 1 pi apart between each one of these because that's a period of a tangent is pi, where n is an integer. Okay? Integers are positive and negative. What type of discontinuities are these? These are infinite. Ooh. They are infinite discontinuities. You'll learn. You guys know me. I don't know how to spell. Infinite discontinuities. They are infinite. If you don't like how I did that, how I graphed that, well, you can say y equals. Remember, tangent is sine x over cosine x. So anytime the cosine equals 0 is a vertical asymptote, isn't it? Well, how do you get that so fast? Well, again, I know my trig. I know my unit circle. Actually, I don't know my unit circle the way you guys did it. I learned it a lot different, but I know these points. Okay, 1, 0, 0, 1, negative 1, 0. I filled it in, and 0, negative 1. And I know these points are listed as cosine, comma, sine on the unit circle. So everywhere I have an x value of 0. Ooh, pi over 2. Ooh, 3 pi over 2. And There's another rotation. See how they're pi units apart? That's why my asymptotes are pi units apart. And from there, I'm signing off for a shorter than normal video. We're going to finish this. We will start by seeing removable discontinuities tomorrow, and we will learn how to remove them tomorrow. Have a good day.